Hello, my name is Dmitry Zakharov. I'd like to welcome you to my talk, and I'd also like to thank the organizers for inviting me and giving me a chance to speak at this conference. So this is joint work with several authors, including my father, who passed away last year. And I will talk about how to construct a family of solutions to the KP1, the Karavantsov-Petvashvili-1 equation. Okay, so first let's talk about the KdV equation. So the KdV equation is the quintessential example of a 1 plus 1 integrable system. So it describes one-dimensional nonlinear waves, such as waves on shallow water. And it has a family of solutions. So first of all, it has the one soliton solution, which is given right here. So it's a solitary wave of a certain height, and it has a velocity which is proportional to its height. And KdV also possesses multi-soliton solutions, which, so if at negative infinite time, you superimpose several solitons of different velocities, and you let them interact. So the fast solitons are going to eventually overcome the slow solitons, and they will all scatter, and the velocities of the solitons are preserved, but they were going to exchange phases. So if at minus infinity you have a superposition of solitons, at plus infinity you also have a superposition of solitons with the same velocity, but with exchanged phases. So the Kp equation is a two-dimensional generalization of the KdV equation, so it describes quasi-one-dimensional nonlinear waves. And it has two physically distinct versions depending on whether or not surface tension or gravity is dominant. So I'll be mostly interested in the Kp1 equation, where this alpha squared is -1. And I'll construct a new family of solutions to this equation. Okay, so first of all, Kp1 and Kp2 are two-dimensional generalizations of KdV, and the first thing you can try to do is generalize the one soliton solution of KdV, and you can do that just by translating in the y direction. So Kp1 and Kp2 both admit a line soliton solution, which is a kind of a translated at an angle version of the one soliton solution of KdV. But it behaves differently in Kp1 and Kp2, so it is stable in Kp2, but it is unstable in Kp1 with respect to small perturbations of the front. Okay, so in Kp2, line solitons are stable, so you can ask, well, can you construct solutions consisting of interacting line solitons the same way that you have interacting soliton solutions in KdV? And so the answer is yes. There's a wide family, a very beautiful theory of interacting line solitons in Kp2. So the simplest is the y-soliton solution, where you have two solitons come in and merge. And so the triple point can't see it, in this diagram evolves linearly with time. And then you can imagine putting more and more line solitons together and seeing what happens. And so there are more general solutions describing interactions of several line solitons. And so they form these beautiful evolving polyhedral arrangements. And there's a lot of interesting combinatorics related to this, cluster algebra, tropical mathematics, and so on. And so what I'm going to do in my talk is to construct a family of solutions of Kp1, which have the same large-scale structure as the line soliton solutions of Kp2. Okay, but I first want to talk a little bit about tropical mathematics, because this is a really good place where this subject can be brought into the theory of integrable systems. So what is tropical mathematics? So imagine taking the field of real numbers, adding -infinity, and introducing different arithmetic operations on it. So instead of when we add two numbers tropically, we take their maximum. So -infinity is obviously the identity element for this operation. When we multiply two numbers, we instead add them, and so of course 0 is the identity element for this operation. So there is tropical division, which is the opposite of tropical multiplication, that is to say it's regular subtraction, but there's no such thing as tropical subtraction, which of course makes life somewhat difficult. Okay, so now that you have this field with this operation, you can introduce tropical polynomials. So what is that going to be? Well, you just take, let's say, two variables, and you start applying tropical addition and tropical multiplication to it. And so the result is going to be what's called a convex piecewise linear function. So it's just a maximum of some collection of linear functions in x and y with integer slopes m and n. Okay, so now that you have the notion of tropical polynomials, you could say, well, what is the zero set of a tropical polynomial? And so the correct definition of a zero set is what's called the bend locus. So the zero set of a tropical polynomial is the set of points where the polynomial is not differentiable. So this is a convex piecewise linear function, and so at the points where it's piecewise linear and not linear, it's not differentiable. And this happens precisely at those points where this maximum is attained by at least two terms inside of it. Okay, so what does this have to do with the theory of integrable systems? So line soliton solutions of Kp2 have the following form. The solution is a second logarithmic derivative of a tau function, and a tau function is simply a sum of exponential functions which are linear in x, y, and t. Okay, so now if you take just a single exponential function and you plug it into a second logarithmic derivative, you get 0. So therefore, near any point in the xy plane where one of these terms is dominant, if, let's say, fm is greater than all of the other fn's, then the corresponding exponential is going to be exponentially dominant. And so then the sum is not really going to notice it, it's only going to see a single term. And so therefore, taking the second logarithmic derivative will give you something that's exponentially small. Okay? So therefore, the solution is supported in a neighborhood of the set of points where two of these f's are equal and are greater than all other terms. And this is exactly the bend locus of a tropical polynomial. Okay? So in other words, from the point of view of tropical mathematics, line solitons of Kp2 are tropical algebraic curves. So these are the zero loci, the bend loci, of some tropical polynomials. Okay, so how am I going to construct solutions of Kp1? So Kp1 equation has a rich family of solutions in what's called Gramian form, which is perhaps less well known than the Wronskian form. So it's also derived from Sato theory. So what are the ingredients of the Gramian solutions? So you take a matrix CJK, which is a symmetric positive semi-definite matrix. And then you take a set of solutions, psi j, which are linearly independent solutions of the auxiliary system to Kp1. So for example, you can take a psi to just be an exponential of the solution phi, which you obtain by taking the Fourier transform. So it's just a linear function in x, y, and t. But more generally, you can take one of these exponentials and you can differentiate it with respect to lambda. So you can just multiply it by any polynomial in x, y, and t that you obtain by differentiating with respect to lambda. And so all of these are going to be solutions of the auxiliary system. Okay, so here's what I'm going to pick. I'm going to pick a few values. I'm going to pick what's called the rank. So this is going to determine the complexity of the solutions. I'm going to pick some spectral values, which determine the velocities. And I'm going to pick what I call depth, which is going to be the highest order derivative in lambda, where having positive depth involves having what are called lumps. So I'm going to talk about that in a second. And I pick a symmetric positive semi-definite matrix CJK. And then I just put everything together. So I take my function psi to be a sum of these exponential functions, which have been differentiated with respect to lambda with certain constants, and I plug this all into here. So it is not easy to guarantee beforehand that your solution is non-singular, so you essentially have to just check this by hand. So one thing you can do, of course, is you can require this matrix to be positive definite, but I will sometimes have it be positive definite, semi-definite, or even zero. So I will verify non-singularity on a case-by-case basis. Okay, so the first thing I want to do is construct what are called lump solutions of Kp1. So in this case, each function psi is a multiple of just a single exponential, and my matrix CJK is just equal to 0. And so if you figure out what happens to this formula, if this matrix is 0 and all these functions psi have the same exponential, you'll see that in fact there's a common exponential term that factors out of the determinant, and so that is killed by the second logarithmic derivative. So for the case that I described, the tau function is actually a polynomial in x, y, and t, and u is a rational function x, y, and t. And so the solution turns out to be localized in the xy plane for all t and consists of certain individual lumps. So lumps are the only known stable solutions of Kp1, and Kp2 does not have any spatially localized solutions. And so I talked a while back that a line soliton of Kp1 is unstable with respect to perturbations, and so it turns out, Polanovsky and Stepanov showed that in fact it decays by emitting chains of lumps. So this is what a single lump looks like. So this was constructed by Petviashvili using a numerical method before any of this theory existed. And then you can imagine trying to take these lumps, scattering them against each other. So one thing you can do is you can first give them different velocities and you let them scatter. So it turns out that when lumps scatter, they do not exchange velocity. Their velocities don't change, but their phases also don't change. So they just kind of pass right by each other. They wave, but they don't even stop to talk. So their phases remain the same. And so another thing you can do is you can take lumps and you can put them together into, you can give them asymptotically the same velocity. And so what you're going to have is solutions consisting of lumps which are weakly bound. So they separate as a power of time, which is less than 1. And so everything turns out to be governed by the Kalayjian-Moser system. And in particular, alpha here can be 0. So you can have solutions of lumps which consist of several lumps that are actually bound, which I think we might call these clumps. So they form these sort of triangular configurations. So imagine billiard balls on a table at the beginning of a set. And so then so they travel in these triangular configurations. And then you can imagine what happens if several of these clumps scatter on each other. So these sorts of solutions have also been constructed. Okay, so what I will instead do is I will construct what are called lump chain solutions. So here I'm going to pick my matrix Cjk again to be 0, depth is 0. And so I take just a single exponential. And so, I take a single function psi with several different spectral values. And so the solution is going to look like this. Okay, so now what does my solution look like? So the tau function has a collection of pure exponential terms and a collection of mixed exponential terms which have these trigonometric modifiers. And I can run the same asymptotic analysis as I did for Kp2. So now I have exponentials, pure exponentials and mixed exponentials. And so if one of these functions f is larger than all others, then the corresponding exponential term is dominant. And so in this large sum here, there's one large exponential term, which if you take the logarithm and then the second derivative is going to give you 0. And so the solution near any point where one of these f's is dominant is going to be exponentially small. So again, the solution is supported near the bend locus of a tropical polynomial, that is to say, near the set of points where 2 of these exponentials are equal and are larger than all others. But now if 2 of these exponentials, if say fm is equal to fn, then it's also approximately the same value as a corresponding term with a trigonometric modifier. So now my solution, instead of being translationally invariant, is going to be periodic in the y direction. Okay, so this is what the solution looks like. So it consists of a set of individual lumps that are all moving in the same direction. So they are the lumps are moving at an angle to the lump chain. And so this solution has been obtained by many authors. Okay, so there is a interesting quantity here which is called the lump flux. So this is simply the first integral of Kp1. And so this is, informally speaking, the number of lumps that are flowing along the lump chain as time goes on. Okay, and so now you can start putting together, just as line solitons is the fundamental solution of Kp2, you can use lump chains to construct various solutions of Kp1. So for example, you can put 3 lump chains together in a triple point, and you can let them interact. And so what happens is that you have these lumps coming from here and from here. And so what they do is they interlace one by one, and they arrange themselves into a new lump chain, which moves in this direction. So the whole triangular picture evolves linearly with time. And at the triple point, the individual lumps interlace. And the local lump flux conservation law is that the lump flux along this chain is the sum of the fluxes along these two chains. And so we get a solution which is visually similar to a Y-type soliton solution of Kp2. But you can also do things that cannot happen for Kp2. For example, in Kp2, you cannot have parallel line solitons. But in Kp1, you can have parallel lump chains. So for example, you can have two lump chains where one of them catches up with the other, and then they just kind of join in. So you have these two solutions, and then you have a single lump chain propagating. And you can also take two lump chains which are parallel and have the same velocity, so you can superimpose one on the other. And so what this looks like is going to be a kind of a quasi-periodic solution along the chain, which is also has no analogs in Kp2. Okay, and then you can start putting together more and more lump chains, and you can construct solutions which whose large-scale structure looks like the line soliton solutions of Kp2. So you can construct an H-type solution like this. So at each triple point, there is a lump flux conservation law. And then you can construct solutions which look like this, which also don't have an analog in Kp2. For example, you can have a small triangle which disappears. That cannot happen in Kp2. And you can have various solutions of this sort. So you can have several different lump chains interact, and so they form these evolving polygonal arrangements, which whose large-scale structure looks the same as the line soliton solutions of Kp2. Okay, and so in all my solutions, I haven't yet taken a derivative by lambda, so my depth has been 0. So if you start introducing positive depth, then what you can have is solutions where the lump chains emit or absorb individual lumps. So here, for example, you can have a lump chain that, as time goes on, it's going to bend a little, it's going to emit a lump, and this lump is going to move faster than the lump chain, and it's going to escape. And so, again, the number of lumps is conserved, so essentially these two lumps interact, and these are the two lumps after interaction. Okay, and you can also construct solutions which consist of lump chains mixed with line solitons. So for example, you can have a line soliton which bends by emitting a lump chain and then bends by emitting another lump chain, and then these two bend points merge, and then you have a single bend point. Okay, and so finally, I just want to show you a few pictures. We can construct solutions which consist of line solitons interacting with individual lumps. So maybe I'll just skip the details and tell you what they look like. So you can construct a solution consisting of a line soliton which absorbs a lump. So a lump is going to move faster than the line soliton and be absorbed by it. Or you can construct a solution which consists of a line soliton which emits a lump. So this is going to look something like this. So this is a line soliton. At some point in time, it kind of bends up and bends forward a little bit, outward, and emits an individual lump. So it turns out that a lump is in resonance with a line soliton if its velocity is 3 times the velocity of the line soliton. So this is what happens in these pictures. So if the velocity of the lump is not 3 times the velocity of the line soliton, the lump can just pass directly through the line soliton. So you can also construct solutions of this kind. So this is a lump that moves from the left, passes through a line soliton, then moves out right. And you can even arrange, since resonance happens when the lump velocity is 3 times the line soliton velocity, you can also arrange to just put a lump directly onto the line soliton. So they're moving together at the same velocity, so the lump is stuck on the line soliton, but they just happen to have the same velocity. Okay, and so finally you can construct solutions which consist of 2 line solitons which are exchanging a lump. So you can think of this as a kind of a quasi-bound state, and this lump as a certain virtual particle which holds these two solitons together. Thank you very much for your time.